Hi, everyone. Uh, Sorry for not being able to make it to Montreal. Um, but at least we can do the session. So let's begin. So today I'm going to present QuickShell. Sharing is caring about an RCE attack chain on QuickShare. This is me. My name is Yair. I'm the security research team lead at SafeBreach. I have more than 7 years of experience in security research. My past research include research on Linux embedded and Android environments, and for more than 4 years now, my main focus lies in vulnerability research in the Windows environment. This is Shmuel Cohen. He is a primary contributor to this research, same as I, so credit goes to Shmuel as well. Now let's see what we're going to talk about today. We're going to start with the reason for why we chose QuickShare as the primary target for this research. Then we'll move on to get a quick overview about a protocol that QuickShare uses. Then we'll see how we managed to fuzz QuickShare and also how we managed to change our research approach and the vulnerability discoveries that came out of it. And finally, we'll also see the remote code execution chain that we managed to assemble from all the vulnerabilities that we found and summarize with takeaways, the GitHub repository, and maybe we'll succeed to have a Q&A session in this scenario. So for those of you who are not familiar with QuickShare, QuickShare is Google's nearby file transfer solution, same as Apple's AirDrop, just like you can see in this picture, for those of you who haven't encountered it. But the reasons for why we chose it are a few. So first of all, Google has recently announced a Windows version of QuickShare, allowing to share files between Windows computers and Android devices using QuickShare. Next, in CES 2024, Google announced that they're working with leading PC manufacturers like LG to expand QuickShare to Windows PCs as a pre-installed app, making it a much more attractive target. Another interesting fact is that QuickShare is able to support a variety of communication technologies. And as far as we knew, it was Google's first time creating such an application for Windows. So it was also probably their first time using the APIs required to leverage these communication technologies. And therefore, we thought that there will be more room for error. Looking for past research, the only one that we could find was done only on the API that QuickShare uses, which is called Nearby Connections API, because QuickShare just didn't even exist back then. It was done only on Android and no CVEs were issued. Another interesting thing to know is that most of QuickShare's code can be found in open source repositories, so that's helpful as well. And concluding all of these facts together led us to evaluate QuickShare as a valuable and likely to be breached target. Our goal was to find the first remote code execution in QuickShare, and to do that, we had to start with investigating the protocol, of course, as it was undocumented. The first thing that we did was to find the two most basic functions that allow to send and receive packets. And following that, we found the read and write functions that were a part of a class called base endpoint channel, which was the base class for all the classes that allowed communication using all variety of different communication technologies. Looking deeper inside the read functions, we were able to see that each received packet is being parsed into an object that was called offline frame. Now, offline frame was really a protobuf object. So for those of you who are not familiar with protobuf, it's basically Google's way for defining structures free of language and then allowing the functionality of compiling them into a specific language with methods that allow serializing and deserializing these objects from and to bytes. So this is the Protobuf definition of offline frame. But don't be alarmed by the name offline frame too much, as offline frame is basically the parent type, the base type for most packets that we'll discuss today. So just think about them as QuickShare packets. And at this point, our first tool for this research was born, and it was called QuickSniff. So basically, the first version of it used PyKD for those of you who know it, but later on, we just created a DLL that was injected into QuickShare on Windows and hooked the read and write functions. Then whenever a packet was sent or received, we parsed the sent or received bytes into an offline frame object and then printed it textually in order to better understand what's happening during the communication. And therefore, I'm now able to provide you with an overview of this protocol. So the first thing you want to know about QuickShare is that it is based on an API called Nearby Connections API. Nearby Connections API is used on Android to discover, connect, and exchange data with nearby devices regardless of network connectivity. Now, QuickShare uses the Nearby Connections API and adds its own implementation over it, which is the intention of Nearby Connections API. Later on, we'll see how. A few interesting facts about Nearby Connections API is that it is based on Protobuf. For encryption, it uses Google's UKey2 library. Then, in order to distinguish each app that uses Nearby Connections API, each app advertises a different service ID that it chooses. And Nearby Connections API supports multiple connection strategies, but today we're going to focus primarily on the peer-to-peer one, which is the one that QuickShare uses. So without further ado, let's see the basic flow of communication using Nearby Connections API and the proprietary implementation that QuickShare adds. During this communication, we have an initiator and a responder. The initiator is the one that sends a file, and the responder is the one receiving it. The communication begins with the initiator sending a connection request, following by a UKey2 client init packet. Then the responder responds with a UKey2 server init packet. Finally, the initiator sends back a UKey2 client finish packet, and then that finishes the UKey2 handshake successfully, basically exchanging keys, ensuring that all subsequent packets will be encrypted. Then, after keys have been exchanged, both devices send a connection response packet indicating that they would like to accept each other's connections. And at that moment, according to the Nearby Connections API, the devices are considered connected to each other. At this point, the proprietary communication of each app that uses Nearby Connections API begins. And when I'm saying proprietary communication, I'm not talking about just random raw bytes that the application chooses, but Nearby Connections API defines a set of packets that you can use when you use the Nearby Connections API. You're not using them just as these packets. It's basically the API that each different method uses different packets. But basically, these are the packets that you can use in your proprietary implementation. So far, we saw the connection request and connection response packets. And from now on, we'll mainly focus on the payload transfer and bandwidth upgrade negotiation packets, because these are the ones that QuickShare mainly uses after the initial connection. So let's see QuickShare's implementation. And just as a reminder, this is where we stopped. just where the proprietary communication begins. So after that, what we saw is that the both devices send a payload transfer packet. Now, looking at the content that is being transferred inside this payload packet, these payload transfer packets, we were not able to quite understand the content, but with the help of another protobuf file that we found in one of the open source projects, we saw that it was actually another protobuf structure hidden inside the body of the payload transfer packet. And this structure was called paired key encryption. Now, at that form, both devices sent a paired key encryption packet inside a payload transfer packet, of course. And then they also did it with a paired key result packet. Now, at first, we didn't quite understand the purpose of this packet because their names were not very indicative. But with the help of a few experiments, we noticed that these packets really enforce QuickShare's device visibility modes. So basically, the device visibility mode in QuickShare defines the entities that are allowed to send files to the device. There are three different visibility modes that are everyone, contacts, and your devices. Everyone is pretty obvious. Contacts means that you can receive files only from your contacts, and your devices means that you can receive files only from devices that are linked to your Google account. Great. So these packets enforce the device visibility modes. After device visibility modes were enforced, the initiator device that wants to send a file sends a file introduction packet with some information about the file that it would like to send. The responder is then prompted with a file introduction dialog with an accept and decline button, and the responder hopefully presses accept in a happy flow. This triggers an accept packet to be sent back to the initiator. Now the initiator knows that the responder would like to accept the file, so it sends the raw file over a payload transfer packet. Great. So now we understand the basic functionality of how the protocol that QuickShare uses looks like from a network perspective. Now let's take a look at how this whole thing looks like from a user's perspective. So we see on the left the initiator, and we see on the right the responder. This is a Windows PC and an Android phone. So the Windows PC chooses the phone that it would like to send the file to. The phone presses accept, the file was received, and now it's located in the download folder. Great. So now that we understand the protocol, we can move on to fuzz it. So for the fuzzing infrastructure, we use the most straightforward one for Windows, which is WinAFL, and for instrumentation, we used DynamoRio. Then, in order to mutate only the values that are contained inside the protobuf structure, we used libprotobuf-mutator, which just does that. It's able to mutate only the fields because we do not want to ruin the validity of the protobuf structure itself. Then after a lot of bug fixes and a lot of hustles, we were able to get the fuzzer up and running. Now, the fuzzer basically fuzzed an entire QuickShare session in each iteration. So on each iteration, it sent about 10 packets, chose a random one to mutate, and then saw the result, moved on to the next one. And as you can see, it was pretty slow. However, even though it was slow, it did yield some interesting results. It resulted 4 reproducible crashes. With that being said, unfortunately, they were not exploitable. Another interesting finding by the fuzzer was a reproducible timeout. This reproducible timeout was located in the logic where QuickShell tries to check whether a file that it is about to receive is already present in the downloads folder. Then the reproducible timeout brought QuickShell into a state where it continuously opens that file in the downloads folder in an endless loop. So that was an interesting finding. We were not able to see how we are going to exploit that exactly, but that was an addition to the reproducible crashes. However, at that point, we thought that it was time for reflection. We did get a fuzzer up and running, but it was pretty slow. It did result some crashes, but they were unexploitable. So instead of continuing to perfecting the fuzzer, we moved on to search for business logic vulnerabilities. And when we started doing that, we just said, boy, oh boy, we wished we had done it sooner. And the first vulnerability that we're going to speak about is the file acceptance bypass that we found. So if you remember, in order for the initiator to send the actual file, it first needs to send a file introduction packet with some information about the file, and it waits for the responder to send back an accept packet. Then and only then it sends the raw file over payload transfer packet. However, thinking about the fact that we saw that QuickShell's code was so generic, complex, and filled with threads and async methods all over the place, we thought, what will happen if we just immediately send the payload transfer packet with the file itself without doing the whole introduction and accept thence? The result was that this actually worked successfully without any issues and without any need for the responder to press accept and actually accept the file. We just sent the file immediately and it was just written to the downloads folder. Not only that the responder doesn't need to accept the file, this also bypasses any device visibility mode. So even if the victim device is set to receive files only from devices that are linked to the same Google account, then we can still place a file whenever we want on that device's downloads folder. So let's see our first demo for this talk, in which we'll see this exact exploitation. So here we'll see the same Android phone that we saw before. We'll see that its downloads folder is empty. We'll move on to the Windows PC, see us running the exploit, and then immediately we'll see the file in the Android's phone's downloads folder. So let's take a look. So we see that this phone is set to receive files only from devices linked to the same Google account. We see that the downloads folder is empty. Now we're moving on to the Windows PC to run our exploit. Now we ran it, and let's take a look at the downloads folder. Here is our malicious file. Okay, I hope you can still hear me. Okay. So this was our first business logic vulnerability. We'll move on to the next one, which was, as I told you, we wish we had done it sooner. And this one was forcing a victim QuickShell device to connect to our, sorry, to connect to our rogue Wi-Fi access point. Okay, so throughout QuickShell's code, there's a term referred to as bandwidth upgrade negotiation. Bandwidth upgrade negotiation is the process of upgrading the current communication technology that is being used in order to achieve better transmission speed. And devices can upgrade their communication technology to a variety of options, including Wi-Fi Direct, Wi-Fi, Bluetooth, WebRTC, NFC, and even Wi-Fi hotspot. So in the Wi-Fi hotspot bandwidth upgrade negotiation, what happens is that one of the devices sends an SSID and a password to the other device, and the other device connects to it. The purpose is that one of the devices will create a hotspot, and then they will communicate over this Wi-Fi network. And as you can assume, probably in the past, researchers have already shown that they can use this fact in order to create a man-in-the-middle attack and force Android devices to connect to their malicious Wi-Fi access point. However, this was possible for about 30 seconds maximum, and since then, this was already mitigated by Google. Today, Android devices do not use the internet through a hotspot that they connected to as part of a bandwidth upgrade negotiation. I hope that you can still hear me. Yeah, just looking if Recon is still on the call. Great. Okay. Okay, so I told you that that this is no longer possible on Android devices. We cannot force force an Android device to connect to our Wi-Fi access point, but it will not use the internet through this access point, so we will not be a man in the middle. Google were aware of this risk, so they mitigated it. However, looking to do the same exact attack and the attack technique on Windows, this was just absolutely possible. So when we force a Windows device with QuickShell to connect to our rogue Wi-Fi access point, the Windows device does use the internet through our Wi-Fi access point. So that means that we can now sniff the internet traffic of every Windows device that uses QuickShell. Great. Okay, so this was our journey of finding most of the vulnerabilities that we found. But we found 8 vulnerabilities in total, but this was still not the holy grail that we were looking for, which was the RCE that I mentioned at the beginning. So with a sentence that we invented while we did our investigations, just like turning standard stones into deadly drone, that sounds pretty much impossible, we decided that we're going to chain these vulnerabilities into remote code execution. As a recap, these were the abilities that we had. We could create files in the downloads folder of the victim remotely without any need for approval. We could force victim Windows devices with QuickShell to connect to our Wi-Fi access point for about 30 seconds maximum. We could also crash QuickShell in multiple ways. And finally, we also found a way to force QuickShell to continuously open a file in the downloads folder of the victim. Just to continuously open a file in the downloads folder of the victim. This was the reproducible timeout, if you remember, that we talked about when we saw the results from the fuzzer. Okay, so enumerating these abilities led us to an insight. The insight was that the location where QuickShell stores its received files is the same place where browsers place their received files, and that's browsers place their downloaded files, and that's the downloads folder. And with that insight comes an idea. What if we could overwrite an executable file that was downloaded to the downloads folder immediately after it was downloaded, just before it's being run? If being a man in the middle can somehow help us know which executable files are downloaded by the browser to the downloads folder, and if we can somehow override these files using our abilities, then this would lead to an RCE, because we'll be able to replace the executable files with our malicious ones, and the user will run our executable. Now, of course, we still did not have these exact abilities, but we had close abilities. Now, just to understand what we were aiming for, so let's take VS Code as an example. What if a victim goes into the VS Code websites, downloads the latest VS Code installer, we then, using our man-in-the-middle attack, somehow understand that the victim downloaded the latest VS Code installer, so we know its name. Then if we can overwrite this executable before the user runs it, then the user will run our executable. So because we believed that the Wi-Fi man-in-the-middle attack might somehow still help us anyway, we decided to start with making it last for more than 30 seconds. To do that, we tried to think of a way to prevent QuickShell from reaching the logic where it returns to its original Wi-Fi network after it performed the bandwidth upgrade negotiation for the Wi-Fi hotspot. And then a very, very simple solution came up, which was just crashing QuickShare right after it connected to our rogue Wi-Fi access point. And that just worked flawlessly. So we forced the victim Windows device to connect to our Wi-Fi access point. We then immediately crash it, so it's not bringing back its original Wi-Fi network, and we get a forever lasting Wi-Fi connection to our, again, rogue Wi-Fi access point. In regards to continuing to exploit QuickShare further after we got that Wi-Fi connection, that forever lasting Wi-Fi connection, this is not an issue. That is because when QuickShare is installed, it creates a scheduled task that runs every 15 minutes and checks whether QuickShare is running. Then if QuickShare is not running, it just runs it. So sometime between 0 seconds to 15 minutes, QuickShare will relaunch. And with this attack, we got the two first links in our remote code execution chain. So we're now able to be a man in the middle forever and sniff the victim's internet traffic. Now, we expected these links to come in handy for identifying names of downloaded executables. So let's see why they were so helpful for that. And this is the reason. Metadata matters. So looking at this image, we thought that it explains exactly how we leveraged this man-in-the-middle attack. Basically, it was true that files are normally downloaded over HTTPS, and HTTPS is encrypted. However, there were still two very important elements in the metadata of an HTTPS session. The first one is a server name indication. So HTTPS is encrypted using the TLS protocol. The first packet in the TLS protocol is the client hello message that is sent from the client side, and this message contains a server name indication extension indicating the domain to which the client is interested to connect. So that means that if we are a man in the middle, then even if the traffic is encrypted and we see only HTTPS, we can still determine all the domains to which the client connects. The second element that is present as part of the metadata of an HTTPS session is the approximate size of data that is transferred in a session. So when a file is being downloaded over HTTPS, it's normally downloaded in a single TCP session. So even though encryption might add some random padding, the amount of data that is being transferred from the server to the client during a download of a specific file stays relatively the same. In addition to that, the size of an executable file is usually much bigger than the size of other pages or resources that may be transferred from a website to a client in an HTTPS session, especially if it's a website that is meant to deliver executables, specific executables or specific installers. The conclusion is that if we know the domain that the client communicated with, and we know that it's a website that is offering an installer, we also know that there is a large file that is being downloaded along with its approximate size, then that means that we can also very accurately guess the name of the downloaded file. So for instance, if we see that someone goes into code.visualstudio.com and downloads 95 megabytes, so we can very confidently assume that this person downloaded the latest VS Code installer. And so we framed and defined our new man in the middle technique more specifically. In order to be as precise as possible, we understood that we need to define what we called domain paths. So a domain path is the sequence of domain to which we expect the victim to access until the download starts. If we'll take a look at Notepad++, then the scenario with Notepad++ is a bit different than the one with VS Code, because when we press down on the download button in the notepad++.org website, we're not downloading the executable from this website. We're really redirected to github.com, which then redirects us to objects.githubusercontent.com, and the executable is ready downloaded from there. So if we'll only look at the final domain, we won't be able to know that that's Notepad++. So we have to follow the entire chain of domains. So to conclude, this is how we defined the new man in the middle technique that we created. We start by creating a mapping between domain paths to executables that match these domain paths and their sizes. Then we wait until the victim hits a certain domain path in a limited time frame, and we start counting the downloaded data. Finally, based on the downloaded size, we deduct the installer's name. And so we chained another link to our RCE chain. Now we can also detect the name of an executable that is downloaded by a victim. But that being said, for the remote code execution, we still need the ability to overwrite files, as we mentioned before. Once we know the name, we need to overwrite it before the user runs it. However, it doesn't have to be a generic ability to overwrite files. It could be an ability that allows us to overwrite files only in the very specific situation that we're in, when files are being downloaded. So what we try to do is to overwrite Google's Chrome's download when it's still ongoing. Now, to do that, let's first understand Chrome's basic download process. So when Chrome downloads a file, no matter which file it is, it starts by checking whether the file that it wants to download, at least its name, is already present in the downloads folder. Then if it does, it decides that the final name for the download will be prefixed, sorry, not prefix, suffixed with an index number surrounded by parentheses. Okay, if the file doesn't exist, so of course it doesn't do that. Then it starts downloading the file, but into a temporary, a file with a temporary name, with a CR download extension. And then when the download is finished, then this temporary file is being renamed to the final name for the download that was decided on at the beginning of this process. So what we thought was that if we send a file in the middle of this process, then if we send a file with the exact same name of the final name for the download, this might confuse Chrome to maybe delete its download and leave our file in place. That is because the final name for the download by Chrome was already decided at the beginning of the process. So what if suddenly there was a file with that name in the downloads folder? But if you remember, in order for us to be able to guess the final name for the download, we need to know that the download is finished because we must have the approximate download size in order to guess the name. In order to be in that situation where Chrome's download is still not finished, but we do know the approximate size of the download, as the man in the middle of this process, we can wait for the last TCP packet from the server to be sent. Then when we get it, we hold it. We're not forwarding it to the client. And at this moment, we know that the download was finished and we know its approximate size, but the victim, the client, still does not know that the download is finished. Chrome still did not rename the temporary file to the final name of the download. So right at this moment, we send our file with the exact same name. As you can see in this example, it's VS Code setup.exe. We sent that file and we tried to do that. And unfortunately, it didn't work. Didn't. So yeah, it didn't work. What we saw was that Chrome just overwrote our executable, so our executable got deleted, and the download was finished successfully. So our idea didn't work. But with that being said, we understood that it's still not the end of it, because all that we need to achieve is a way to somehow prevent Chrome from being able to overwrite the file that we sent. And if you remember, there was still one ability that we haven't leveraged at this point, which was the reproducible timeout that the fuzzer found that allowed us to bring QuickShell into a state where it continuously opens a file that we choose from the victim's downloads folder. So what we thought is that if just after we send our executable to the victim, to its downloads folder, we also force QuickShell to continuously open that file, the exact file that we sent, then maybe Chrome will fail to overwrite it. That is because it is being used at that moment. So giving a try to this idea, we saw that it actually worked. And it was actually the best scenario that we hoped for. Once Chrome finishes the download, the result is that it deletes the temporary CR downloads file. It fails to overwrite our malicious file. In its user interface, it reports that the download was finished successfully, and when the user clicks on the downloaded file in Chrome's downloads window, then this actually runs our malicious file. And this concludes the remote code execution chain that we were so hoping for, um, bringing success to our goals. And finally, we prepared a demonstration video that will present this entire remote code execution attack chain, so you can see it complete. So let's watch it. I will say that the video starts with the attacker's perspective. So we'll see the attacker's computer. We'll see the attacker setting up a hotspot. Then we'll see the attackers searching for victim, chooses a victim, and then we'll move on to see the victim's computer. So let's start. So we see the attacker's hotspot. We also see its IP. Now we are running our tool. We found a potential victim called test machine. Moving on to test machine, we see that it's connected to a safe breach access point, but now it's being disconnected and connected to test AP, which is the attacker's access point. And now the attacker is able to see all the domains to which the victim accesses. Now the victim browses into the Spotify website in order to download the latest Spotify installer into its downloads folder. Now the download has started. We'll see it finishes in a moment. The victim runs it, and you've been pawned by the Safe Breach Labs team. Now let's do the same thing with Notepad++. So the victim goes into the Notepad++ website, downloads the latest installer, and let's see what happens. Okay, so the download is now finished again, and our malicious executable runs instead again. The remote code execution that we were aiming for. Okay, so I know it all looks so dreamy, like every single vulnerability that we found was relevant for this remote code execution chain, but actually we found two more. They were just not relevant for the chain. So the first one was a limited path traversal that allowed only to create a file in the parent folder of the downloads folder, but it had to have a very specific name, so it was not very helpful. And we found another denial of service vulnerability based on one of my previous research projects. Overall, at this point, we found 10 different vulnerabilities, reported all of them to Google, of course, which cooperated very well. They issued fixes for everything. And of course, after fixes are issued, we usually try to test them. And most of the fixes did work, fortunately. But there were two surprises still. So the first surprise was in the patch for one of the denial of service vulnerabilities that were found using the fuzzer. This vulnerability, this crash was caused basically due to invalid UTF-8 continuation bytes. You don't have to understand what that means, but the example that we provided, to Google with invalid UTF-8 continuation bytes, I mean an exception that was raised due to this error was caused due to a file name that starts with a null terminator. This was the example that we provided. Google's patch for that was to verify that null terminators do not exist in file names. So of course, this can be bypassed by just placing other different invalid UTF-8 continuation bytes in file names, and then you get QuickShell to crash again, of course. But this was not the biggest surprise. The biggest surprise was in the way that Google fixed the vulnerability that allowed to create files remotely without approval. What they did was that instead of not creating the files in the first place, they just deleted them after they were written to disk. They identified them as unknown files. As you can see here, two files. The file is created after we send the exploit, and then it is deleted, as you see in this video. But what they did was to search for these files that they identified as unknown files, and later on delete them when the file sending session is over. The way they identified the files was with their payload ID. So what we did was to send two different packets with two different file names and two different contents. However, set the same payload ID for both payload transfer packets. We hoped that Google will think that we sent only one file while two were created, and the result was that it actually worked. So we sent these two files, and only one got deleted. So let's see the final demo for this session, which is the exploitation of this bypass. So we're running our updated exploit. Two files are now created, and only one got deleted. We still have our malicious file on the victim machine. Okay, this was Google's official response after our original report. We thank them. They were very cooperative and they fixed all the issues. Oh, sorry. Yeah, we were here. They fixed all the issues. Overall, they issued 3 different CVEs. The first 2 ones were issued after our original report, and the last one was issued after the next report when we reported about the bypasses. So we covered pretty much everything about the technical flow, and now it's time to talk about the takeaways, which are just as important. Our first and most significant takeaway is that standard stones may sometimes be forged into deadly drones. And what we mean by that is that as hackers, you often have limited tools at your disposal. You might have achieved something, but it's not exactly the thing that you were aiming for. Now, when we reflect on our research, we believe that even seemingly basic or unimpressive abilities can still sometimes be transformed into something much more powerful. We're all familiar with the typical chains of vulnerabilities that address known issues like bypassing stack cookies or other memory corruption mitigations, but it's not always so straightforward. Sometimes you might have unconventional abilities like forcing an endless loop to repeatedly open a file. These abilities can be used to create very unconventional flows and still allow you to somehow achieve your ultimate goal. The next takeaway shifts to the defensive side. So many products leave known issues and bugs unfixed because of prioritization. Now, often these issues seem to pose no security risk or only a minor one that doesn't require the immediate attention of the development team. However, addressing these known issues, bugs, or minor security risks can sometimes be the crucial thing for mitigating a much larger risk that you might not be aware of. Because as you can see in our case, for example, if we did not have the denial of service vulnerability that caused QuickShell to crash, we wouldn't have been able to establish a stable Wi-Fi connection, which would have completely disabled our remote code execution chain. Lastly, it's crucial for vendors that develop software to focus not only on specific programming mistakes like memory corruption bugs, When you evaluate a program security, it's important to take the broader perspective and consider whether simple logic or intended behaviors might also introduce security risks, much like the bandwidth upgrade negotiation that allowed us to connect a remote victim to our rogue Wi-Fi access point. And with that final takeaway, I want to thank you all for joining me to this session. Um, Here you can scan the QR code of the QuickShell repository, which contains all the tools that we saw here today, including the full exploitation chain that we saw in the demo. Um, these are the social media details of myself and Shmuel Cohen. And basically, this is it. Thank you all for joining. Are we having a Q&A session or we finish here? Any questions? We're muted. Okay, I'll stay here in case we are having the Q&A session. Any questions? Thank you, everyone. That's very nice. Sorry for not being able to be there, but hopefully I'll submit another work and be there next year. Okay, thank you.